Assalamu alaikum. I welcome you all to another lecture on power electronics. Previously, we have covered three modules of power electronics, which were the basic module where we covered the devices. Then we moved on to the module related to the DC to DC converters. And lastly, we discussed the DC to AC inverters. In the today's class, we will discuss the analysis of conventional rectifiers, which converts the AC waveform into a DC waveform. Let us start with the lecture on rectifiers. Rectifiers are the devices which convert AC into DC form, and they are based on the diodes. In this particular lecture, we will not discuss the controlled rectifier, which are based on the silicon control rectification, and by varying the alpha we control the output voltage. Here we will discuss the rectifiers and we will try to understand the necessity of studying these AC to DC rectifiers for this power electronic course. Previously, most of the students have studied the rectifiers in their first course on electronics, which is usually entitled Electronic Devices and Circuits in Pakistan. In that particular subject, the application of diodes was the main target, whereas the analysis with respect to the different loading conditions and the total harmonic distortion because of the rectification process was not discussed. Here we will discuss these rectifiers for various type of loads, and we will progress in such a way that we will discuss first of all the very basic type of a half wave rectifier circuit with only the resistive load. Thereafter we will develop the loading conditions to more complicated loads. So let us start with the rectifier. The first rectifier that we will start with is the half wave rectifier. They are seldom used in most of the circuits because of their low efficiency. And all the other performance indices are also very poor. For example, the THD, the efficiency and the performance is quite poor. However, this is a device upon which the foundations of the full wave rectifier are laid on. Here we do not have an average supply current equal to 0, and therefore for most of the applications it poses problems for transformer based applications because of the non-zero average supply current. However, this circuit is quite easy and simple, as I will draw it here, and it gives a very good way to initialize the mathematical treatment of the rectifier circuits. So we have, let us say this is our supply. This is VST, which is equal to Vm sine omega t. We only have one rectifier here, we only have one diode here, and here we have this resistance. This is a very simple circuit. We have this V naught, this is ID, this is plus minus VD. So as you can see that if we apply the basic theory of a diode, so the diode should work when we have the positive half cycle. So if I draw the waveforms here, the waveforms are very simple and quite basic. So we have if this is the supply waveform, this is Vs of t. Then for each positive half cycle, we shall have the output voltage available across this resistance R, and consequently there shall be only the output current shall only flow when we have this diode in the forward bias condition. So in this particular arrangement, the output voltage is quite simple. So we shall only be having this at the output without having any negative portion here. This is V0, and the rest of the negative half cycle, or the rest of the remaining portion of this particular AC waveform is blocked by the diode, and consequently this negative voltage appear across the diode. This is the VD. Now if you notice here that we have not converted this entire cycle of an AC waveform into a DC, rather we are only utilizing one half of the available cycle. Therefore the average output voltage V0 is given as, if we apply this expression 1 over T integral 0 to T Vt dt, and by the way these are all omega t here, because omega t is quite a good method of having the x-axis independent of the frequency. So this V0 is equal to V average. So if I simply integrate this one, this is 1 over 2 pi. So this is pi, this is 2 pi. So we have 0 to pi Vm sine omega t d omega t, and this gives us a value which is equal to Vm over 2 pi into 1 plus 1, and that is equal to Vm over pi. Now because it's a resistive load, so the current I shall follow the shape of the V0. However, the amplitude of the current may be slightly different. So we can say this is the I0, and consequently we have the average output current. Average output current I0 is equal to V0 over R, and that is simply equal to Vm over pi R. Further to this, if we note here that the power which is absorbed by this resistance is not only the DC portion, but the waveform contains the AC part as well and the AC component as well. Therefore, to compute what is the power which is absorbed by this particular resistance, we need to have the RMS value of the output voltage as well. So the Vrms square is equal to 1 over T integral 0 to T Vt square to dt, which is equal to 1 over 2 pi 0 to pi Vm sine omega t square d omega t, and that is equal to Vm over 2, and this is the Vrms, and consequently the IRMS or the RMS current is equal to Vm over 2R. So now once we have the values of the RMS voltage and the RMS current across the load, the power absorbed by the load is equal to I square RMS into R, or consequently we can also use this V square RMS divided by the resistance R. For this particular waveform, if you see here, we cannot compute the power factor of this particular rectifier, and therefore to solve for the power factor, this power factor is equal to P naught divided by the Vs RMS into Is the RMS. Now for this particular rectifier, as I have said that this efficiency is quite low, since we are not at all having any utilization of, we are not utilizing anything from this negative half cycle, therefore it has low efficiency. So if I write down the efficiency equals to the PDC over the PAC, then this is equal to V naught into I naught divided by the PAC, which is the Vs RMS into Is RMS, and that is equal to this V naught is equal to Vm over pi, and here we have Vm over pi r, which is the output current. So V naught is equal to Vm over pi multiplied by Vm over pi r divided by the RMS value, which is equal to Vm over 2 multiplied by Vm over 2r, and this is equal to 40.53%, which is quite a low value. So therefore, despite having that the peak inverse voltage rating for this diode is equal to the V maximum, this is the peak inverse voltage rating, this type of a rectifier is seldom used. As we have seen, this low efficiency is of no use for most of the practical applications, and therefore it is seldom used in any real life applications. Now let us move ahead and complicate the circuit by adding a different loading condition. So let's have a series R plus L load instead of having only a resistive load, because these type of resistive loads, they seldom exist in a real world, and for most of the practical applications these resistances are in fact a representation of a power factor corrected loads, right? So there we have, with the power factor corrected load, we can represent it by a pure resistance, but mostly in industry or in some real life application, pure resistance is a very rare case of the load. So with a series RL load, the circuit becomes a little bit complicated. So now we have the same diode. Here we have this resistance and this inductance. This is VST, that is equal to Vm sine omega t. This is plus minus, this is Vd. Here we have the Vr, and this is plus minus, this is equal to Vl, and combined we have the output voltage V naught appearing across this complete RL series load. Now this circuit brings in some very interesting aspects of the loading conditions, such that it extends the connection time of a diode. So now if you see here that if this diode is forward biased, if this diode becomes forward biased, then this is a circuit which is the equivalent circuit under the forward bias conditions. Now this circuit is a well-known circuit that is well studied in the earlier course on circuit analysis, and this represents a first order load which is energized by a sinusoidal source. So whatever the current which is flowing here, I of t, it can be expressed by the application of the KVL here. So if I apply the KVL, I know that this is VR, this is VL, and this is VS. Then by the application of the KVL here, we have VST is equal to VR plus VRT, and that is equal to RIT plus L DI over dt. And this differential equation, this first order differential equation, its solution is very well known, and we do know that if we treat this equation some like like we did for in the circuit analysis course, it has its own transient part and our own steady state part. Then the transient part under steady state condition has to vanish, whereas the steady state part remains with the system. So the overall current IT is a function of the force response and the natural response, which occurs because of the existence of this RL circuit here. Now this force response, as you all know, this corresponds, or it represents the steady state response of a given circuit, whereas this circuit INT is a transient response which vanishes out with the passage of time, and it has to vanish out if the system is a stable system. So the force response here is quite simple. If I want to calculate what is the final current flowing in this particular circuit, then this IFT is nothing but is equal to the peak value Vm divided by the impedance offered by this RL load, this RL load, and because we have an inductive load here, so the current shall have some phase difference, which is represented by this theta. Now what is this Z? We earlier know that this Z is equal to R square plus omega L whole square, and this theta is equal to tan inverse of omega L over the resistance R. However, about this INT, this natural response, we do know that if we have a first order circuit, like this R plus L load, this I of t is equal to A e to the power minus t over tau. Now this A depends on the initial condition of the circuit, and if we know the value of this A, the solution becomes a particular solution. Otherwise, it is a general solution for this first order differential equation. And remember that for an RL load, this tau is equal to L over R. So now if I combine these two with this force response and this natural response together, I get the value of the current. That is equal to Vm over Z sine omega t minus theta plus A e to the power minus t over tau. So to find out the value of this A, we will apply the initial conditions here. So in this particular circuit, prior to the positive half cycle, this diode is reverse biased, and therefore there is no current. We assume that there is no current flowing here in this inductance, and therefore this the IL 0 negative is equal to 0. This is the initial condition. Now this initial condition, when I apply in here, that we have I 0 negative is equal to 0, and of course it cannot change instantaneously. Then by putting this t equal to 0, this is equal to Vm over Z sine omega t is 0 minus theta plus A e to the power 0, and this gives me the value of A, which is equal to minus Vm over Z sine of minus theta, and this can be represented as Vm over Z into sine theta. So now if I substitute it back into this above equation for this IT, then this IT becomes equal to, this becomes equal to Vm over Z sine omega t minus theta plus sine theta e raised to the power minus t over tau. And in terms of the omega t, this becomes equal to Vm over z sine omega t minus theta plus sine theta e raised to the power minus omega t over omega tau. And this is valid only for the positive half cycle. Now to understand the waveforms, because the waveforms are a little bit tricky here, so what I have done is that I have simulated an example from the textbook over which the key waveforms of the circuit are plotted. This red waveform is representing the input voltage, so this is Vst, whereas this blue waveform which is flowing here, it represents the load current I naught. Notice here that because of the values of the inductance and the resistance for the given example, the amplitude of this current was quite low, and therefore it was multiplied by a factor of 10 to have a zoomed view of this waveform. Here we have, this is pi, and here we have this is equal to 2 pi. Now there are two important points for this given circuit. The first important point is that because of the presence of the inductance here, we are having a current flow longer than the duration of this positive half cycle, which ends at pi. Also we can see here that the current flow is having a phase delay, whereas this particular time instant we have the peak value of the implied AC waveform, and here somewhere here we have the peak value of the current which is flowing through the load, and therefore this is the theta, which is the phase difference between the applied AC voltage and the resultant AC current. Other than that, if we look down on this particular graph, there are two important points here. That this seems bizarre at a very first instant, but if we closely look onto this thing, the current starts rising from this particular value, which is this 0, and it has a positive half cycle. It has a positive slope till it reaches its peak value. During that whole duration, the voltage across the inductor stays positive. As soon as we have the current having its negative slope here for this duration, the current slope is negative, then according to the inductor, we have VL equals to L di over dt, and with this di over dt negative, the inductor voltage shifts onto the negative side, thereby creating a voltage difference which keeps the diode in a conduction mode for a period which is longer than this particular pi. We should note one thing we should notice here, that for this particular circuit here, this diode, if this is the A and this is the K, then this VAK should be greater than 0 volt for an ideal diode and greater than 0.7 volt for a silicon diode, or 1.1 volt for a power electronic diode. Once we have this difference available, this diode will stay in the conduction mode. So right after the pi time, if you see that this VL is enforcing enough negative voltage that the cumulative anode to cathode voltage for this diode remains above its threshold values, and consequently it conducts beyond the positive half cycle, thereby connecting this voltage source Vs to the load for the duration which ends at this particular time instant that I will call as beta. These, you know, waveforms which are quite interesting in showing you the inductor voltage and the output voltage at every instant of this particular circuit. Although it looks a little bit bizarre, every instant on these waveforms is a validation of the Kirchhoff voltage law, as I have shown here. So what is this? Here I have actually shown a subtraction of the Vs minus the Vr minus this Vl. So for this entire loop I have applied the KVL, and if you see here that during the positive half cycle we have this KVL applied such that the sum of the voltage rise is equal to the sum of the voltage drop, and hence it is equal to 0. For the negative half cycle, because the device conducts beyond this this value which is this pi here, so beyond this we have, once the current is equal to 0, whatever the voltage is left for the AC waveform, it is blocked by this by the diode, and hence it appears across the diode, and this is the peak inverse voltage rating of the diode, which is the peak value, which is something equal to 200 269 or something 270 volt. So irrespective of the system that we have seen here, irrespective of the waveform, we now know that the inclusion of the inductance in the load actually introduces a new complexity in the system, whereby the conduction of the diode extends beyond the value of pi, and consequently it poses its own challenges in solving the circuits where we have the where we have the R plus L load. Moving on with this thing, now that we know that we have a point where the current becomes equal to 0, and I have said that this is equal to beta. This beta is known as the extinction angle, and we are interested in calculating the value of this beta using using some circuit analysis techniques. So if I substitute, or if I put this beta value into this I omega t, such that this omega t becomes equal to beta, because if this is the omega t axis, then this is the beta value of this omega t, and at that instant this I beta is equal to Vm over Z sine beta minus theta plus sine theta e raised to the power minus beta over omega tau, and that should be equal to 0. This is equal to 0. So if I have a little bit of mathematical manipulation here, then this sine beta minus theta plus sine theta e raised to the power minus beta over omega tau, that is equal to 0. Then this particular equation, gives me the value of the beta for a given circuit. But now if you see here, this is not an equation which can be solved without using any numerical analysis tool. This theta can be calculated by the application of the tan inverse expression. We know that for an RL load, we have stated above that this theta is equal to tan inverse of omega L over R. So everything else is known, but we have two betas here, and therefore we require to have some numerical analysis method here, which can be easily plotted in MATLAB. I will shortly show you the waveform of that MATLAB function to calculate the value of beta for any given values of the circuit. So now for this given circuit, because we have an inductance as well as this resistance here, only the resistance, only this R, it consumes the average power, because the average power across this inductance is equal to 0. But for that, if I want to know what is the average power consumed by the R, I should know what is the RMS value of the current which is flowing here. And unlike the circuit which is discussed above, in here it should be calculated for this entire duration of the current, and therefore the IRMS is computed from 0 to beta for this particular circuit, which was the only from 0 to pi for the circuit where only the resistance was made part of the scheme. Having said that, let us have another variation in the load and say that we have this R plus L plus source load. Now this is another variation in the loading condition. We still have this single diode here, this inductance, and here we have a DC source. So this is plus minus VDC, this is VLT, here we have the VRT, and this combined becomes equal to the output voltage V0T. And here we have, this is VST, that is equal to Vm sine omega t. So if we include this VDC here, then one thing is very sure, that for this AC applied voltage waveform VST, and for this VDC, this is this VDC, then the diode will not conduct until and unless we have this sine wave greater than this VDC, because otherwise the potential difference across this particular diode will not exceed its value, so that it goes into the conduction mode, and therefore the diode remains reverse biased. Diode remains reverse biased for VST greater than for less than the VDC. So this means there is a value on this omega t axis. There is a value on this omega t axis after which the diode becomes forward biased. So let us say that this particular value is known as this alpha. So this implies that the Vm sine of alpha, when it becomes equal to this VDC, then ideally, if the diode is an ideal diode, it can go into the conduction mode if the anode to cathode potential is equal to 0 volt. Then for using this particular expression, we can get the value of alpha equals to the sine inverse of VDC over this Vm. Now once the diode starts conducting, then we can apply the KVL here. So for diode forward biased, if I apply the KVL, then this is Vm sine omega t is equal to RIT plus L dit over dt plus VDC. And again, for the same circuit, we have to apply we have to go for the natural and the step response to find out the overall response of this given circuit. Now, the force response here, this IFT, which is a steady state part, it consists of two different sources. One is for the AC source, and the other one is for the source which is connected at the load, which is the DC source. So their combined effect shall be force response for this given circuit. So here you can see that for this AC response, it is we can use any expression for that we have studied in linear circuit analysis. But let us say we can go with the superposition theorem, that we short circuit for the superposition theorem we short circuit the AC or the DC voltage sources, and we apply by applying each source at a time, we get the values of the independent responses against those sources, and then we add them together to get a cumulative response. So this is equal to Vm over Z sine omega t minus theta. And for the DC source, because we are only having because when the diode is conducting, then the current is in this particular direction. So when we will apply the superposition theorem for this VDC, it shall have a value with a negative sign, and that is equal to minus VDC over R, because the inductance for against this DC source becomes equal to 0. So this is the force response for the circuit where we have the R plus L load. As far as this natural response is concerned, I and T, that is a e to the power minus t over tau, and you can see here that for this particular expression, we have this I omega t is equal to Vm over Z sine omega t minus theta minus VDC over R plus a e to the power minus omega t over omega tau, and this is for alpha is less than omega t is less than equal to, and this is 0 otherwise. Now if we apply the initial condition, then we can find out the value of alpha. And what is that initial condition? That I at alpha equal to 0, this is the initial condition, and therefore A becomes equal to minus Vm over Z sine alpha minus beta plus VDC over R e to the power alpha over omega tau. And for this particular expression, the value of the current or the shape of the current is, it starts from this alpha, it starts from this particular alpha, and it goes all the way and it ends somewhere at the beta, which is way beyond this value of pi. And we shall have the same behavior across the inductance in terms of the inductor current and the inductor voltage. So what is the average power for this circuit? In this circuit, there are two components which can get the power absorbed. Here we have this resistance R, we also have a DC source VDC. Therefore both of these two components share the portion of the average power absorbed. So for the power absorbed by the resistance or by the resistor, it is equal to I square RMS into R, and for the DC source we have it equals to I naught into the VDC, where this I naught is the average current or the DC current, average output current. Now if we notice here, for all the circuits where we have studied the inductance as part of the loading conditions, the main important point here is the output voltage, which goes negative for the portion beyond pi. So it actually reduces the overall output voltage of the rectifier, which reduces the already tarnished value of the efficiency. So for that, there is a concept which is known as the freewheeling diode. To get rid of the negative part, which is occurring as a result of the inductance in the circuit, whenever we use and in inductance, whenever we have an inductive load, we provide a freewheeling diode for the inductor current to flow whenever this main diode becomes off. So this is V naught T, this is VRT, and this is VLT. So now we have two diodes, D1 and D2. Now if this D1 is on, then this particular point A is positive with respect to this point B, and therefore this D2 is off for the entire duration when this D1 is on. As soon as we have the negative half cycle appearing across this D1, the D1 becomes reverse biased. As the D1 becomes reverse biased, in order to have the current flowing into the same direction, this VL reverses its polarity, and consequently it turns on this diode D2. So when D1 is off, then we have the D2 on, such that we have a short circuit across the load during the entire negative half cycle. So during the positive half cycle, we have this type of a circuit. This is for the positive half cycle, and during the negative half cycle, this is the loading conditions. So the voltage across the load becomes equal to 0 for the negative half cycle. But what it eventually do is that it get rid of the negative portion which is appearing on the output voltage, and consequently it actually increases the output voltage available at the output. So here we have this is the V naught for the positive half cycle. Then for the negative half cycle, we have a short circuit path, therefore the voltage is equal to 0. And then we again have the positive half cycle as a result of the forward biased operation of this D1. Here we have this, if we have a continuous output current here, if the current is continuous, because just like the inductance studied in the DC to DC converter, here we also have the continuous and discontinuous mode of operation for a rectifier. So for a continuous connection mode of operation, so this is the wave shape of the diode D1, and for the rest of the time, this diode D2 actually conducts, which is something like this one. This is the diode D2. So for the current flowing through ID2 and this ID1, we can clearly see that they share the burden from 0 to pi, and then the D2 takes on the charge, and it allows the current to flow free will through itself from the duration from pi to 2 pi. Now if you notice one thing here, that all of these half wave rectifiers, they have sort of a complex output voltage waveform and the current waveform. Therefore the Fourier method or Fourier series is used to quantify the performance of the different harmonic contents which are present in a given system. You cannot find out the value of the RMS voltage unless you have the information about the AC component which is flowing in these given waveforms. So for that, a generic wave value of the Fourier series is used for a rectified sine wave. This is equal to Vm over 2 sine omega naught t minus n is equal to 2, 4, 6 to infinity. This is 2 Vm over n square minus 1 pi into cosine n omega naught t here. Now this waveform, as you see, this is the DC part, this is the fundamental component or the first component, and this is only for the even harmonics. So based on this thing, we can estimate the values of the RMS current flowing through a given circuit. For example, in this above circuit that we have shown here, let us say that we have this R equals to 2 ohm, inductance is 25 millihenry, this V maximum is equal to 100 volt, and if the frequency is equal to 60 hertz, we want to find out what is the power which is absorbed by this resistance, right? So I want to see what is the total power here, what is the power absorbed here or supplied by the source. So for that, first of all, I will calculate what is the value of this Vm over pi, which is this V naught. So it is 100 divided by pi, it gives me a value equals to 31.8 volt. Then I can also calculate the value of I naught, that is equal to V naught over R, and that is equal to 15.9 ampere. So the load power is equal to I square RMS into R. How can we find out this IRMS? We need to find out the amplitude of the rest of the component. So for that, this V1 is equal to Vm over 2, and that is equal to 50 volt, right? This is from this component. About the V2, we have this 2Vm divided by n square minus 1, and that is equal to 2 square minus 1 into pi, and this gives me 21.2 volt. Similarly, I can find out the values for this V4, that is equal to 4.24 volt, and then I can get the value of V6, that is equal to 1.82 volt. Now, based on these values of the voltage, I can find out the value of the current I, such that this Z is equal to R square plus omega L square and omega L square. So for this, the Z naught, which is for this V naught, that is equal to 2 ohm, because we do not have this inductive part for the DC component, so it is straight away it becomes equal to 2 ohm. For the fundamental component V1, this Z1 is equal to 9.63 ohm. By putting this n equal to 1, omega is equal to 2 pi f into L. So we have the total impedance offered by the first harmonic constant is Z1 equal to 9.63 ohm. Then we have Z2, that is equal to 18.96. Then we have Z3 equals to 37.75 ohm, and Z4 becomes equal to, sorry, this is not 3, this is 2, and then we have this is equal to 4, this is equal to 4, and this is equal to 6, and that 6 we have equal to 56.58 ohm. So you can clearly see that the impedance is rising, and consequently the current for each is 0, each actually reduces. So I naught is equal to 15.9. Then we have I1, that is equal to 5.19. Then we have this I2, that is equal to 1.12. Then we have I4, that is equal to 0.11. And for the value of I6, we have equal to 0.03 ampere. Now to find out what is the IRMS here, IRMS, we will use an expression k equal to 0 to infinity, and this is IK into RMS. To find out this, and we need to convert all the values other than the DC value here into the effective value. So that is equal to 5.19 divided by under root 2 whole square plus 1.12 divided by under root 2 whole square plus 0.11 divided by under root 2 whole square, and this gives me a value that is approximately equal to 16.34 ampere. So based on this thing, the power which is absorbed by the resistor is equal to I square RMS into R, and that is equal to 534 watt. So the THD for this can also be calculated by this particular expression, I square RMS minus I1 square RMS divided by I1 square RMS, and this, by using this particular expression, you can find the value of the THD. So one thing is here that if we want to reduce the harmonics here and we want to have an average load current which is entirely constant, something like this one, because the job of a rectifier is to provide constant output. So if I make this I naught something like this one, this means that I naught is equal to V naught over R, but we have the inductance available here. So if I look onto this particular circuit, if I want to create this type of a waveform, I do know that the average load current is controlled by the resistance. However, the inductance has its impact on the load current with the AC quantities, and therefore to get rid of the AC component present in the output load current, we can make this XL equal to infinity, and that means that this inductance should be high enough that this current becomes equal to a constant value. So therefore for this particular value, I naught T is approximately equal to I naught, that is equal to V naught over R is equal to Vm over pi R, if we somehow create this L over R, or the time constant, equal to infinity. So this almost DC current can be realized by making this L of R greater than the time period of this particular waveform. And of course this is with a freewheeling diode, and if this happens, then this becomes the shape of the current through the diode D1, and for this we have this equal to the ID2. So this by increasing the time constant tau of a given RL circuit, we can actually reduce the load current harmonics for a given rectifier scheme. We will discuss in the next class the half wave rectifier with the C filter, and we will also try to uncover the aspects of the controlled rectifiers, controlled half wave rectifier. So till then, take care. Allah Hafiz.